So back in 17a, we were introduced to one of the growth models being logistic growth. And now that we're in 17b, we're going to take this kind of an extra step and look at logistic growth as a differential equation. Well, what defines logistic growth is that we start off with a per capita growth rate. So dn dt, that differential equation, is telling me how my population n is changing over time. We call that the growth rate. And when we add in that phrase per capita, what that means is that we're looking at the growth rate relative to the overall size of the population. Or I'm looking at that growth rate divided by n. Another way that we can write that is to say dn dt times 1 over n. There are a lot of different per capita growth rates, but the logistic growth rate in particular assumes that this per capita growth rate is a linear function. And in particular, it assumes that this per capita growth rate is a decreasing linear function. So if I think about my axes here as being n and our per capita growth rate, or dn dt times 1 over n, then what the logistic growth model suggests as a model is that when n equals 0, the growth rate would be some fixed value of r. But that growth rate, that per capita growth rate, would decrease linearly over time to have a growth rate of 0 when the population had reached k, or a carrying capacity. Now there are a couple of things that I want to point out here. Well, n equals 0 would mean that there were no organisms. So it's unlikely that if we have no organisms, that magically more organisms will spring from nothing at all. But remember, as with a lot of calculus, we're really talking about this as a limit. Now it makes sense that this would be our largest value for the per capita growth rate, because whatever that growth rate is, we're always dividing by the population size n. So as that population size grows, we do expect this, it's kind of logical that because we're dividing by that population size, that this is going to become a smaller value as that population grows. So the other key characteristic of that logistic growth per capita growth rate is that this linear function decreases to 0 when we've reached some value that we call k, and say that's the carrying capacity. And you've probably heard that term in biology classes before. So we can really quickly model what this linear equation looks like. We know that it's got an intercept of r for our vertical axis and an intercept of k for our horizontal axis. So if I were just thinking about this as a y equals mx plus b sort of equation, then this would become y equals, now my slope, rise over run, or in this case we're going down r and over k, so a negative r over k times x plus r. Putting that into the variables that we're actually working with in our equation here, our y-axis is really that per capita growth rate, or dn dt times 1 over n, and that decreasing linear function, I'd have negative r over k. Our x-axis here is actually our population value, or n, plus r. This is the model for the per capita growth rate for the logistic equation, but it's not usually the way that we see it written in the textbook. So in the textbook, we're going to factor that r out to be left with negative n over k plus 1, And then, like a lot of textbooks and mathematicians tend to do, for some reason, people have decided that having a minus sign out in front is less visually appealing and less simplified than switching this order to look like r times 1 minus n over k, and there's our dn dt times 1 over n. And this is our standard differential equation form for logistic growth.